Yeah, let's get started with structured prediction basics. So the idea here behind structured prediction is there's a lot of different prediction problems that we want to solve in NLP related tasks. So we have I hate this movie, I love this movie, and we select very bad or very good. These are the things that we're very familiar with to the point that you're all tired of seeing this example. So the reason why I noted this is because there's lots of different types of prediction tasks. The simplest one is binary classification, where we just want to select negative or positive. So we have two choices, and we basically want to select yes or no. The second one is multi-class classification, where we have, I hate this movie, and we want to go to very bad, and we have 5 classes here. And then the one that we're interested here is something where we have an exponential or infinite number of potential answers. And these are the structured prediction problems. So these include things like part of speech tagging or translation, for example. So for the first one, how many possible labels do we have here? How many possible outputs do we have? Oh, sorry. Yeah, so first, second. For the third one, how many possible labels do we have? But, sorry, when I say labels, I mean how many possible outputs do we have? It is exponential. What? Yeah, so the number of labels to or I'll call V, the vocabulary of labels, to the length of the sentence, which I'll call this. So this is how many possible answers we have, because we have the possibility of one tag for each of the words, and then we have the combination of all of them. So for the second one, how many possible answers do we have? Infinite, yeah, exactly. Because we could generate an infinitely long sentence if we really wanted to. So in reality, we don't do that because that crashes our programs when we try to do that. But theoretically, it could be infinite. So this is called structured prediction. It's not called like exponential class prediction or something like that. So why do we call it structured prediction? And basically the reason why is the classes are too numerous to enumerate. So we need to have some sort of method to exploit the problem structure so that we can enumerate these effectively. And an example of this is that these two outputs are very, very similar. They only differ in one class. So the way we would predict these would be, similar. So when we say structured prediction, it doesn't necessarily mean we have a tree structure or a graph structure. It just means that we have some sort of, we know something about the problem that allows us to not predict all of these classes independently. So there's many varieties of structured prediction, both in terms of models and in terms of learning algorithms that we use for these. And I'm going to cover some subsets of all of these. So in terms of models, things with RNN-based decoders are performing structured prediction. You take an encoder and you predict the words in the output, or you predict the tags in the output or something like this. So why is this structured prediction? The reason why it's structured prediction is because you don't predict the whole sentence at the same time. You predict one word at a time. And by that, you're exploiting the fact that the first word in the sentence influences the second word in the sentence, which influences the third word in the sentence. And we can kind of predict them incrementally like that. Also, convolutional and self-attentional decoders, which I talked about in the previous couple times, these also are similar. They predict one word at a time. The first two are basically, here they're called autoregressive models. Autoregressive models are models that take in an input and generate the output based on the previously generated input. They're also called history-based models. If you see that, they basically mean the same thing. Another thing that I haven't talked about yet, but I'm going to be talking about in a few classes, is conditional random fields. So conditional random fields are different from RNN-based decoders in that they make local independence assumptions, which allows you to basically train them with dynamic programming type algorithms, which is not the case for RNNs. I won't talk about that a lot because I'm going to talk about it in detail in a few classes, but just be aware that this is another type of model that you can use. For training algorithms, there's all kinds of training algorithms. Structured perceptron and structured large margin, I'm going to be talking about this class. Sampling corruptions of the data is kind of an approximation to a structured prediction algorithm, which I'll also talk about this class. Exact enumeration with dynamic programs, it's like what we use to train CRFs, and I'm going to be talking about that later. And also reinforcement learning or minimum risk training. These are also methods that you can use to train these, which I'm going to talk about later. So one thing I'd like to caution people about is I'm going to talk about lots of structured prediction algorithms. These are all good algorithms that you can use for different problems that you're interested in. It's very common for people to try to use reinforcement learning for everything because it's kind of what people know or it's kind of what's hot right now. In many cases, it's a really bad idea to use reinforcement learning because there's much better algorithms that can exploit the structure of the problem in a better way. In some cases, it's very good to use reinforcement learning, and I'll try to make the distinction between those. So, are there any questions so far? No? Okay. So I'll talk about an example structured prediction problem. As I said, there's lots and lots of these problems, but I'll use sequence labeling as an example. So in sequence labeling, we have one tag for one word. For example, for part of speech tagging, we go from I hate this movie to preposition, verb, determiner, noun. It's also very common to try to label spans. And when we label spans of things, like for example for named entity recognition, it's very common to reduce the problem of labeling spans, like Keanu Reeves, into a beginning and in tag or an O tag. So what this means is here we have a person starting at this word and it continues until we get another B tag or an O tag. So even if you want to predict something like a span, you can still treat this as a sequence labeling problem, and this is very common to do. So the easiest way to do this is independent classification. So basically what this is doing is, let's say we want to do this in the simplest way possible. What we do is we basically pad our sentence, and then we take all of these words, turn them into vectors using word embeddings or something like this. Then we have a classifier. And this classifier predicts preposition or something like this. So this is very simple. If you want to call it a convolutional network, you can call it a convolutional network because it basically is. So what we do is we step over, we predict the next one, predict the next one, predict the next one. But basically the idea is we look at the two surrounding words in the current word and we predict the part of speech tag. So this is super simple. This is a structured prediction task. So we are using, we're trying to predict something where basically all of these tags kind of interact with each other. So it's a structured prediction task where we could exploit the structure of the problem. But basically what we're doing is we're breaking down the structured problem and changing it into multiple independent multi-class classification problems. So this is not what we normally call structured prediction because we're basically not exploiting the structure in any way. So are there any questions here? Is that fine? Yeah. Okay. So now I'm going to talk about sequence labeling with a BILSTM. So instead of just taking these word embeddings, we run a big BILSTM over this, and based on the BILSTM, we take its hidden states and we predict all of these tags with the classifier. So now the big question here is this kind of a structured prediction model? Now we're looking at all the words in the input. Who thinks yes? Who thinks no? Oh, very equivocating. Okay. So this is a little bit tricky. So in general, this is not modeling the output structure. The outputs are independent. So normally we would not call this kind of a structured prediction algorithm. This would still be a multi-class classification algorithm. And the input is here over. Or we do a complicated thing over the input, but we don't actually model interactions between the output variables. So a kind of rule of thumb here is if you're calculating the probability of any yi given only x, this is not normally called a structured prediction problem. But if you're calculating the probability of yi, and it depends on something else, like let's say it depends on all of the other y except for yi, or let's say it depends on all previous yi. Let's say it depends on y1 through y minus y to I minus 1 and x. Then this would be kind of a structured prediction model. Yeah.
So I might be confused a little bit.
Mm-hmm.
Why wouldn't that be considered a structured prediction task? Because if you're making the classifications based off the hidden states, then don't the outputs depend on each other?
No, they don't, actually. So the hidden states are calculated solely from the words in the input. At no point are we feeding in the predictions into calculate the hidden states. So one really good kind of distinction that you can make is anything that you can calculate deterministically from the input without actually feeding in any of your predictions, without ever taking an argmax, basically is not in the realm of structured prediction. And the moment you take an argmax and calculate something, or some approximation of the argmax, then that becomes a structured prediction. Anything else? Okay. So why would we want to model interactions in the output? A good example of this is, let's say we have time flies like an arrow. So time flies like an arrow is an ambiguous sentence, as I'm sure you know. So we have a bunch of interpretations: noun, verb, preposition, determiner, noun, 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 verb, determiner, noun, verb, noun, preposition, determiner, noun, etc. Oh, so yeah. Pretend you didn't see this. So which one corresponds to the actual proverb? Yeah, the first one. Yeah. So this is basically saying time flies, and it flies like an arrow. Number two, what is this?
Time flies things like an arrow.
Yes. So time flies are a particular type of fly, and they really like arrows. And then the third one. What is it? Yeah, so you're telling somebody to measure the time. Please measure the time of flies similarly to how an arrow would measure them. So this is a classical sense of ambiguity. So the interesting thing here is all of these are kind of, let's say our model didn't really know which one of these was better. It didn't know the proverb. So based on that, it kind of needs to make a decision about which one. But if it doesn't consider the structure, probably the ideal decision is to say number one is a noun, because it's a noun in two of our interpretations. Number two is an NNS, which is because it's NNS in two of the interpretations. And IN, number three is IN, because it's IN in two of our interpretations. So if we take the max frequency, we get something completely different that doesn't even have a verb in the sentence. So just making each of these decisions independently is, not ideal on the structure level, because it gives us, something that doesn't make sense as a sentence whatsoever. Yeah, so the interpretation of this is time flies that are similar to an arrow. Yes. Yeah. time flies, which are the type of flies. So let's do a really simple tagger that actually considers the structure of the output and considers our previous decisions. So the easiest way to do this would be just to feed in our previous decisions when we calculate our neural network states, our hidden states. So by doing this, this is very similar to the encoder-decoder model that we talked about before. We generate one thing, and then after we've generated that one thing, we feed it back into the network to update our hidden state. So this is, let's say this is our encoder-decoder model, but for tagging. It's not a common model that you see because there are better models for tagging, but it's one that you could use. Yes. So given this, the simplest way to train this model is using something called teacher forcing. So the idea behind teacher forcing is basically, it's another name for maximum likelihood estimation using the tags that you already have in your training data. So in other words, you just feed in the correct previous tag, the tag that you used that exists in your training data last time. Yeah.
Also, the test time you do the auto-regressive
Yeah. So look.
but in test time you don't have the correct position. So
Right. So that's exactly the important point here. So at training time, we just feed in the correct tag, and then at test time, we feed in the predicted tag. And this is a problem, which is what the whole rest of the class is going to be about. But during training time, you're assuming your previous tags have been correct. At test time, you cannot assume they've been correct because you obviously don't have the correct tag. So I have some examples of this. Let me see if I can pull them up real quick. Somehow my code has magically disappeared from my computer, so I will not pull them up. Sorry, go ahead.
So why can't we use the same, like feeding previous prediction to your next input during training?
So I'll talk about that later. That's one way we can fix this problem. Not fix, but it's a reasonable idea that's not always optimal. Yeah. So I don't have any code for this, but because I have no idea how this code disappeared from my computer. But it's on GitHub, so you can go and take a look at it if you'd like to. So the question got ahead of what I was going to talk about, but the reason why this is a bad idea is because the teacher forcing is assuming we're feeding in the correct previous input, but at test time we may make mistakes. So if we get PRN and this is correct, that's fine. But if we get a noun, a plural noun here, then we feed this in. Suddenly we're going to be getting into a situation that we've never seen at training time before. We're going to get something wrong. And because we get something wrong, these errors continue to propagate until the very end of the sentence. And we get huge mistakes and problems. So for example, maybe in this case, we'll get noun, plural noun over and over and over again. So the kind of technical term for this is exposure bias. This is a very widely used term in structured prediction. And the idea behind exposure bias is the model has only been exposed to correct inputs in the training. So it has a limit in the types of things it has been exposed to. And then suddenly when you put it in the test time, it gets exposed to other things. So it sees things that it hasn't seen before. Are there any questions about this? No? Okay. Another kind of term that we should be familiar with is local normalization versus global normalization. So locally normalized models, basically what happens here is each decision made by the model has a probability that adds up to 1, which can be expressed in this equation. And I'll explain the equation in a moment, but after I give you the contrast. So globally normalized models, these are also called energy-based models. Each sentence has a score, and this score is not normalized over a particular decision. So instead, it looks like this. Let me close the door. So hopefully that gave you some time to take a look at the equations here and find the difference between them. So basically, the model above is a model that we've been used to seeing before. So this is the language model probability, or the encoder-decoder probability, where we generate one word at a time, and each word is generated according to a softmax, according to a normalized probability distribution. So on the other hand, on the bottom, basically what we do is for all of our hypotheses in our output space, so maybe it's this v to the x hypotheses, the v to the x number of tags that we can do. We first calculate the score for each of these hypotheses by maybe calculating the score over all of our independent decisions. Then we normalize over all of those. So this is an important difference from the point of view of structured prediction models. And the reason why is because let's say we have a model that can only make certain decisions at any certain state. So let's say we have RIB. Actually, it would be better if we had like RIP or something like this, like RIP in Rob. So let's say we have a language model or a translation model that can only generate things that are in our dictionary, would be one example. And once we go from R, once we go to one of the states, R, or the bottom R, we only have one decision. Because we only have one decision, a locally normalized model has to give a probability of 1 to that decision, because the probability of the decisions has to add up to 1. So of course, in the top, we will give probability of I given R a probability of 1. In the bottom, the probability of O given R. For some reason, once we've gotten into the state, we know we really don't want to generate O. We don't like O in this context. However, because we have no other options, we still need to make this equal to 1. And because of this, basically, once we've gotten to the state, we have no way of penalizing this state. And I can give an example. Let's say the score of I given R is equal to 10. And the score of O given R is equal to minus 10. Still, when we take the softmax and we normalize them, of course, this is going to be 1 because we only have one decision. So actually, I'll call this R1 and R2 because the top R is R1 and the bottom R is R2. So if this is the case, then regardless, we have no way of penalizing this bad decision, even though we know its score is low. However, if we added up all of the scores and then did normalization after adding them up, we could penalize the one because the overall score at the end after we did the addition would be much lower for the second hypothesis. So this is called the problem of label bias. So this is the problem of preferring model states that have few decisions. Sorry, there's an extra decisions here. So, so basically we can, when we step into a state that doesn't have very many decisions, this state gets favored. So actually, I'm sorry, this example here, I took this from a paper, but I just realized it's not a very good example. So let's say we have B and we have R, and then we have A, and then we have U, and then we have D, and then we have E, and then we have D. So here we have 2 decisions after B, and we have 1 decision after R. And basically, after B, we'll be splitting the probability between these decisions. But for R, we will not be splitting the probability between anything. So this R doesn't get penalized as much as B does. Yeah, sorry, I realize this slide is not the ideal way of saying this, so I'll try to fix it for next time. Is this clear here? Yeah. Yeah. Let me give a concrete some concrete scores here. So let's say the score of B in this context is 5, and the score of R in this context is also 5. The score of A in this context is 2, and the score of U in this context is 1. And then the score of E in this context is minus 20. Like, we really don't like the word red, or RE for some reason. And then the score of D in this context is 2, and the score of D in this context is minus 10. So what happens is here, because both of these are 5, when we take the softmax, we'll get 0.5 and 0.5, if we take a softmax at this point. Here, when we take the softmax, I'll be completely random and say 0.66 and 0.33, even though that's wrong. And then here, when we take the softmax, we get a probability of 1. And then for the lower one, because we are taking the softmax over 1 element, we get a probability of 1 and a probability of 1. So in a locally normalized model, if we have scores like this, basically what happens is this one will get a probability of 0.5. RED will get a probability of 0.5. BUD will get a probability of 0.1666, etc. And BAD will get a probability of 0.33333. So based on this, the locally normalized model will be picking this red thing here. On the other hand, if we look at their scores, the score of BAD is 9, the score of BUD is 8, and the score of RED is minus 25. So based on this, we know that that RED should be worse. And then in a globally normalized model where we don't normalize until the very end of all of our decisions, we would be picking BUD instead. So the reason why globally normalized models could potentially be better is basically when you get into a really bad state and you realize that you want to be taking back decisions that you've made before, this globally normalized model will allow you to do that easily, where a locally normalized model will not allow you to. Is that clear?
Yeah, so can you give an example where it's the other case where you have a locally normalized model doing better than globally?
Oh, so globally normalized models subsume locally normalized models. So any locally normalized model is a globally normalized model. The difficulty is exactly this, that it's hard to train locally normalized models, which is why we like to use locally normalized models. So I'll talk about that later. Are there any questions so far? No? Okay. So basically the problem with this, training globally normalized models, is that the denominator here is too big to expand naively. So obviously, we can't take the sum over all of our possible options because our sum is v to the length of the sentence. It's exponential or it's infinite or something else. So we need to do something else. And specifically, we can do tricky things. One thing is to consider only a subset of the hypotheses. So instead of considering all the things that go into the denominator, considering only a subset of them. Another thing is that we can design the model so we can efficiently enumerate all of the hypotheses. And that's what I'll be talking about when we talk about like CRFs or other models. So is that okay for now? Okay. So the first one I'll talk about is the structured perceptron. So this is a kind of the simplest model. This was also in the reading if anybody did it. There was a quiz today, so I'll assume that some people, there was no quiz today, so I'll assume that some people didn't, and some people did. But to explain it a little bit more simply than the book, basically the idea here is basically we find the one best, we do search for the best sequence, or the best structured output. And then if the score is better than the correct answer, adjust the parameters to fix this. So specifically, we have this algorithm. It's 4 lines. It's not super complicated. But basically what we do is we find the one best output. So we do our search for the best structured output, which we will call y hat. So this is the one that has the highest score. Then if the score of the highest scoring hypothesis is better than the score of the true hypothesis, so this y without the hat is the true hypothesis, then we do an update, where basically we update in the direction of the true hypothesis and we update away from our incorrect hypothesis. So the idea here is this is the gradient of the, this is the gradient that will increase the score of the true hypothesis, and this is the gradient that will increase the score of the found hypothesis. So we subtract this. So we are trying to minimize this and maximize this. Yeah?
This can be applied in either case of globalized or localized.
You could apply it in locally normalized models, but I've never heard of anybody do that. Usually this is something you do to train globally normalized models. And I think the reason why is because there's easier things that you can do for locally normalized models. So the score function, you can calculate it in any way. You can create a neural network that assigns a score to each decision. This could be the thing that you would normally put into your softmax, but you don't put it into a softmax. Basically.
That's the reason why it was frustrating, because you're not computing the partition function.
So let me be clear. So in the locally normalized models, you calculate the partition function over each decision.
No, I meant for the global.
This is a globally normalized model, and the reason why is because you're not actually calculating the partition function. What you're doing instead is you're only calculating the score for a single best hypothesis, which you get through search. We can also frame this as a loss function. So we really like loss functions in our neural networks because if we can define a loss function, we can optimize it extremely easily by just doing backward over the loss function. So what the structured perceptron loss function looks like is simply this. It's the max of 0, and the score of the highest scoring hypothesis versus the score of the true hypothesis. So if the score of the highest scoring hypothesis is higher than the score of the true hypothesis, then basically we get a loss. Otherwise, we don't get a loss. Let me say one more word and then I'll answer your question. So do we actually need the max? you know, if we take the highest scoring hypothesis and it's equal to y, if y hat is equal to y, then we don't need this max because, you know, it's going to be 0 anyway. I'm putting the max here because it will help us relate this to other things that we'll talk about later. So if that answered your question, then no? Okay, yeah.
So here we are trying to match the score between our best hypothesis and the ground truth hypothesis, right? But does that mean that our hypothesis itself matches the ground truth?
In this case, no, because you could have multiple things with the same score. And then depending on how you break ties, you could have different different scores. So that's one thing here. You'll notice in the algorithm. Here. I wrote different things in the code. In the green explanation over here, the code's actually correct. So normally in the structured perceptron algorithm, you penalize the model. If there's any hypothesis that's greater than or equal to the true hypothesis. So in other words, in this case, you will penalize even if they're equal. This is not actually exactly equivalent to this loss function here. So in this one, if you don't make any updates, then your highest scoring hypothesis will be the true hypothesis. But in this, with this loss function, you might have ties. In the case of ties, then you might not be. Yeah.
So if you have to do search to find your best sort of solution, isn't that like as costly as just calculating the partition function? What makes that cheaper?
Oh, so that's a really good question. So if we have to do search, why is that any cheaper? And the reason why is because this is structured prediction, and we can do search in a way that exploits the problem structure. So we can do something like greedy search. We can do something like beam search or something like that to find this. So we can't calculate the argmax exactly, but we can approximate it. Yeah. Any other questions? So we can calculate it exactly in other situations, like the CRF type models, which I'll talk about later. So that's a distinction between these two. Yeah.
Just for my clarification, if you're doing something like a beam search,
Uh-huh.
will you keep all possible hypotheses which the beam is for the argument, or only pick the best?
So after you've done beam search, the highest scoring hypothesis that you found is the one you'd be using in the arguments. Yeah.
So actually, this type of update method seems to be very similar to like contrastive divergence or something. I mean, would like sampling be also useful in this case?
So yeah, so contrastive divergence is a method that's basically like this, where you do sampling according to a probability distribution, and then you update towards the true sample and away from towards the true answer and away from the sample that you got from randomly sampling from your model. Contrastive divergence only works when you have a probability distribution over your models over your latent variables that you can sample from. It's also very slow because you're sampling normally. So the difference between that and the structured perceptron is this doesn't have to be a probabilistic model. Actually, it could just be a model that assigns scores. It also doesn't require sampling. It takes some max. I'm not exactly sure how that would affect, but I'm pretty sure that taking the max is more efficient when you're training this model. So yeah, so sorry, yeah, the gradient of this function looks like the perceptron algorithm. So I just wanted to mention that also. And this is a normal loss function. We can just plug it into any neural network model. One caveat is that you do need to take the argmax in addition to calculating the score of the true candidate. So this is definitely slower. It's at least 2 times slower than just training normally with maximum likelihood estimation. It's often more than 2 times slower. So that's one thing that you should be aware of. Yeah.
So when you're doing maximum likelihood estimations,
Yeah.
you always have to normalize to get a probability, right?
Yeah.
But for this, you don't necessarily need to do. You can just work with the logics and get the artifacts.
Exactly. So there is a very small benefit of not having to do a softmax. But compared to that, calculating the full neural network for 2 sequences, the true sequence and the argmax sequence, is generally more expensive than that. So to be absolutely clear, if calculating the softmax is very expensive, then maybe this would be less than 2 times slower. But I don't conceive that being the case in most normal models that we use. Okay. So let's contrast the perceptron and global normalization. So basically, if we look at our globally normalized probabilistic model, it looked a bit like this. So we took the score for the entire sequence and we normalized it by all of the sequences that we could be generating. On the other hand, for the structured perceptron, we have a loss that looks like this. So we have our one best sequence and we have our correct sequence. So if we had something like a global structured perceptron, or we had something like a structured perceptron that enumerated over everything, it would basically look something like this, where we would be summing over all of them and calculating the score for all of them, and then summing this to get our loss. But in reality, we don't do this. We just do this for one. So that's why we're able to get rid of this sum, which would be too costly to compute, and actually do this in a reasonable amount of time. Yeah, so the bottom one would have the same computation. So is this clear? Yeah. Okay. So one thing to note when you want to use this structured prediction type loss function, the same goes for any structured prediction type loss function that requires kind of approximating a globally normalized model. Basically, neural network models have a lot of parameters and a big output space, so training is hard. And there are trade-offs between the training algorithms. So selecting just one negative example is inefficient. And the reason why it's inefficient is because basically you're selecting one negative example. Maybe, let's say this was the case and we had bad, bud, and red as our options. So if we select bad and bud, or we select bud as our true one and bad as our highest scoring one, basically we'll only be penalizing the difference between these 2 high scoring hypotheses. We'll only be penalizing the difference between A and U. However, let's say red, instead of its score being minus 25, its score was 8.5. So if this is the case, 8 is the one that we actually want to have the highest score. We maybe give a slight boost to bud, a slight penalty to bad. And now the score gets to be 8.1 or 8.3 and 7.2 or something like this, just arbitrarily choosing our post-update weights. And this one doesn't change or barely changes at all. Now, despite the fact that we did an update to fix the ones that we found, this one is still broken, right? So now we have to do another perceptron update to penalize this one that's still worse. On the contrary, something like teacher forcing or maximum likelihood estimation will penalize all of the bad examples at the same time because it's enumerating over all of our things in our vocabulary. So because of this, teacher forcing is able to efficiently update all of the parameters for all of our vocabulary items, all of our options. But the problem is it suffers from things like exposure bias and label bias. So there's a really simple thing that you almost always use when you're using something like structured perceptron, large margin, teacher forcing, etc. Reinforcement learning, etc. Which is you first start updating with maximum likelihood estimation using teacher forcing, and then after you've done doing that, then you fine tune with a more complicated algorithm. This is especially true for things like sequence models. For things that are slightly less complicated, like tagging, you might get away with not doing this, but this is a very common thing to do. So again, I don't have the code, but if you want to look up what the perceptron algorithm looks like, you can take a look here. Are there any questions about this? All set? Okay. So now I'll talk about a very, very useful thing, which is hinge loss in cost-sensitive training. So this is a no-brainer question that should be relatively easy if you've taken a machine learning course. But let's say we have the dotted line here and the dashed line here, and we want to be separating these circles in x's. Which line is better? The dashed line, yeah, and why? Yeah, it has a larger margin. It's not making as many close calls, or the closest call it's making is not is farther away from all of the others. So the important thing here, though, is that all of them have 0 perceptron loss. So even if even the dotted line will not get any penalty according to the perceptron loss because it's not making any mistakes. So a way we can fix this is instead of taking the perceptron loss, we take the hinge loss, where the hinge loss is basically saying, this is the difference between the good and bad hypotheses. The perceptron only has a loss when the difference between them, or when the score of the good hypothesis is higher than the other one, than the correct one. Sorry, the score of the highest scoring hypothesis is higher than the correct score of the correct hypothesis. While the hinge loss has a loss even if the score is not higher, but it's within a margin of, say, 1 here. This is the hinge loss where, in addition to the score of the correct hypothesis, of the highest scoring hypothesis, we add a margin of m. Where this is not the highest scoring hypothesis, but it's the highest scoring hypothesis that is not equal to y. One thing that you can be aware of is that up until now we've been using the softmax, and we've been calculating the log probability according to the softmax. One extremely easy way to incorporate this into your model that's completely independent of structured prediction is basically anywhere where you have a softmax, instead of using the softmax, you use a hinge loss. And this can be better in some cases. If you train it well, my experience is if you train it well, it's generally better. But it's a little bit harder to train because the loss fluctuates a lot more during training and it doesn't decrease as smoothly. But this is the super easy way to incorporate the hinge loss into your models. If you describe this in DINET, it's basically a single line change of code. Now, the more interesting thing is not just using a hinge loss, but the cost-augmented hinge loss. And the idea here is that sometimes some decisions are worse than others. So for example, let's say we mistake a verb into let's say we mistake a VB, which is the verb base form, into the VBP, which I believe is participle. Anyone know Penn Tree Bank well? I think it's the participle, but I'm not 100% sure. So mistaking a verb into another verb is not so bad. It won't break like the entire structure of your downstream applications. But mistaking a verb into a noun is really bad. This will, completely break things if you try to do things downstream. So the idea here is that the cost-augmented hinge defines a cost for each incorrect decision and increases the margin for mistakes that are really, really bad. So we define a cost between y hat and y, and we add that to our score. So based on this, basically the score, let's say we have VB, VBP, and NN, and the original scores are 5, 4, and 3. And then we also have our cost. So obviously the correct answer has a cost of 0. Maybe VBP has a small cost of 0.5, but NN has a large cost of 5. Because this would be a really bad mistake. So we add them together, and we get 5, 4.5, and 8. And now we will penalize for being too close to NN, which allows the model to be very conservative and try to not make these mistakes as much. So this, maybe this is not related to structured prediction at all, but when you want to apply this to structured prediction, you can define a cost over sequences. And one cost over sequences is your 0-1 loss. So basically, if you have two sequences that differ at all, like BAD, BUD, RED, and let's say BUD is the correct answer, then your cost will be 1, 1, and 0. So your cost being 1, 1, and 0, this is basically exactly the same as the regular margin. It's like a non-cost augmented margin because you'll be having a margin of 1 regardless of what your output looks like. So this is how you define it. Another thing that you can do is Hamming loss. So let's say we have BAD, BUD, and RED. Basically, what the Hamming loss says is all the differences, you sum up all the differences between the strings, and that's your Hamming loss. So of course it's 1 and 0, and in this case it's 2 because we have 2 of them incorrect. So we define it this way. And then of course there's lots and lots of other losses that you can define on a task-specific basis. So we can define stuff like edit distance. We could also do 1 minus blue score if we want to use blue score for machine translation, for example. So what the structured hinge loss does is it's a hinge loss over sequences where you try to update away from the largest margin violation. So what we do is basically, instead of taking an argmax over the score itself, we take the argmax over the score plus the cost. So what this means is, let's say our scores look like this. And then this is cost. Our scores look like this. Instead of doing an argmax, Instead of doing an argmax over the score itself, in which case we would get bad, we do an argmax and get red here because the score plus the cost is equal to 3, which is the highest one. So the reason why this is good is because this basically allows us to find things where that are both high scoring and really bad. And both high scoring and really bad are the things that we want to really penalize and make sure that we reduce their score. And based on this, we can also define a cost-augmented hinge loss over sequences that looks something like this. So then the problem here is, how do we find the argmax above? How do we calculate this? And the answer is, in some cases, in some particular cases, where the loss can be calculated easily, we can consider the loss while we're doing our search for the best hypothesis. Is this clear? Are there any? I'll explain how to do search, but in a second. But are there any questions about this? No? Okay. So the way you can do cost-augmented decoding specifically for Hamming loss, this is super simple. And you could implement it in a part-of-speech tagger relatively easily. Hamming loss, you can see, is decomposable over each word. So each word, if you make a mistake, you gain 1 Hamming loss. So the solution is basically what you do is you add a cost to each incorrect choice during search. So if this is our score over all our choices, what we do is we add 1 to everything, else. And then we select the argmax according to this 1 plus the model score. So normally in this case, because the model predicted the correct answer with the highest score, we would pick PRP during search, but instead we push it away from the correct answer and force it to select NN. So this is really good. So we talked about teacher forcing before. This is like a really, really mean teacher who makes every question as hard as possible. So like every time you make a decision, the teacher tries to trick you into saying the other thing. And only if you're really, really confident do you get the correct answers. So this is like evil teacher forcing or something like that. We should, sounds a lot cooler than cost-augmented decoding. So feel free to use that in your next paper. Are there any questions about this? And then once we do this, we just update according to something that looks very similar to the perceptron loss. And we have an example of this in the code. So these are all kind of very nice principled methods to resolve this. They're especially good for things like tagging tasks, where you can decompose the loss using Hamming loss or something. There's also a bunch of other ways that people use, particularly in neural networks, that are kind of like approximations to these kind of ideas. They're good because they're very easy to do often. They're bad because they aren't, they aren't as principled as the previous ones. But I'll explain them anyway because they're widely used and you should be aware of them. So structured hinge loss is good, but it has a few problems. So considering fewer hypotheses makes this unstable. It also requires decoding, which can be a little bit slow. And you often use pre-training for things like sequence-to-sequence models, so it's not as stable as something like teacher forcing. So one remedy to this is sampling mistakes during training. So this was a method. This is basically a method called Dagger. So this method called Dagger was actually made by Jeff Gordon, who was at CMU until very recently, and now is at Microsoft Research, I guess. But anyway, the idea, it's also known as scheduled sampling because there was another paper that called it scheduled sampling in kind of neural network land. But basically the idea is super simple. In addition to calculating your loss function, you also randomly sample something from the probability distribution. So every time you calculate your loss function according to the true answer, but instead of sampling, but instead of using the true answer to input back into your neural network, you input a random sample. The idea behind the schedule in the name scheduled sampling is basically you start with teacher forcing and then you gradually introduce these mistakes. So this is similar to what I talked about with pre-training. You have kind of a pre-training schedule where you gradually phase this in. And the reason why is if you started out with just random noise, completely random noise, it wouldn't be able to learn pretty much anything. So how do you choose the next tag? And basically the answer is you can either use the gold standard like this, or you can use something called a dynamic oracle. And the idea behind a dynamic oracle, this is particularly useful for parsing. Basically, it's the thing that, it's the tag that might not necessarily be the correct one for the next decision, but it's the one that will get you closest to being back on track after making a mistake. This is particularly important for things like parsing, where some actions, based on the previous action that you took, only some actions are allowed, and you might get to a state where you can't choose a particular next action. However, scheduled sampling has a kind of problem, or Dagger scheduled sampling has a kind of problem, and the reason why is if you think about something like translation. Let's say we have the dog. Dog ate my homework. And for some reason, your model chose randomly sampled dogs at the very beginning of the sentence. So what you do is you calculate your loss function and say, okay, dogs should be turned into the. But then when you calculate your next hidden state, you feed in dogs and calculate your next hidden state. But then what you're saying is, okay, I've seen dogs once. What should I do next? I should predict a dog. So you're saying, you're essentially saying the correct answer now is dog's dog ate my homework. So this is kind of a big problem because obviously dog's dog is a bad idea. It's not a good sentence. So for things like part of speech tagging, this might be a reasonably good idea, but for things where you have reordering or multiple words becoming one word, there are probably better ways to do this. Another thing that you can do is instead of inputting a particular sampled word, you just completely drop out the word. So the idea here is you feed in the input some of the time, and sometimes you just feed in a zero vector that has no information whatsoever. So the reason why this kind of makes sense and may make more sense than scheduled sampling is basically what you're saying is, I want the model to be robust in the face of missing input. But I'm not going to tell you what the actual input is. I'm not going to say it's something that it's not, but I'm just going to not tell you. And if that's the case, you can still use you can still use it to influence your decisions, but you won't use incorrect things to influence your decisions and throw things off. Yeah.
Can you learn when to drop out the input?
Can you learn when to drop out the input? You might be able to. In general, you don't. But that's an interesting idea. I don't know if anybody's ever tried that. So you might want to drop out the input when it's when you're uncertain, for example, and not drop out the input when you're not uncertain. Hey, yeah, that's a good idea. So yeah, this helps ensure the model doesn't rely too heavily on the predictions. Are there any questions about this? No? Okay. In a final solution, this is a relatively recent paper that's actually pretty interesting if you're interested in these things. But the idea is that you corrupt the training data. It's a method called reward-augmented maximum likelihood. And the basic idea is that you randomly sample incorrect training data, then train with maximum likelihood. So the idea is you sample this, a mistake, where you switch verb phrase into noun, verb into noun, and then you just train on this using maximum likelihood. So this is very strange if you first hear about it, right? You're basically adding noise to your training data. And adding noise to your training data seems like a really bad thing, especially if you're training with something like maximum likelihood. But according to the derivation here in the paper, you can say, given that the sampling probability is proportional to how good the output is, so if you sample good outputs more frequently than you sample bad outputs, according to some distribution, you can show that this does something, maybe not directly minimizing the risk, not directly minimizing the number of errors that you make, but kind of going in the appropriate direction towards minimizing the number of errors that you make. So the good thing here is that because you're not even running your model to sample these mistakes, you can sample these mistakes extremely efficiently. So this is basically almost as fast as maximum likelihood estimation, but it's a way of kind of, fixing the exposure bias problem in a semi-principled way that's very easy to implement. So yeah.
So if this works, something like say label smoothing, does it work as well?
So label smoothing is something else entirely, and label smoothing is very effective. I actually didn't mention it here, but label smoothing, basically what you're doing is normally what you're trying to do is if you have the correct answer is A, and then you have B, C, D, E, F. This is a very strange vocabulary, but or very strange order for your vocabulary. But let's say A is your correct answer. Normally, what you're trying to do is you're trying to maximize the cross-entropy with respect to the one-hot distribution, which is also equivalent to log likelihood. But instead, what you're doing is you're multiplying this by some coefficient. This is a hyperparameter, and then you interpolate this with the uniform distribution. So this would be 1 divided by 6, 1 divided by 6, 1 divided by 6, etc. And the idea here is if you optimize towards this, you're encouraging your model to be very confident in its predictions. You're encouraging it to basically output 1 if it's very confident. And by kind of smoothing this off a little bit, you're making it less confident. So this is, in a way, kind of tackling the exposure bias problem, because it's saying don't be so confident in your predictions, but it's doing it in a very different way. And I myself don't know if there's any theoretical connection to the other things that we talked about here. But that's a good question that I haven't thought about enough to give a good answer. This tends to work really well also. So if you're interested, you can look up label smoothing. So, are there any other questions?
Do this kind of ideas work in multi-class, multi-classifications?
Hinge loss, yes, works very well. Label smoothing works very well. Any other ideas? Other ideas that are based on like multiple decisions, structured decisions, aren't applicable there, but unless you have some sort of structured classification space, like a tree structured classifier. But yeah, Hinge loss and label smoothing. And stuff like word dropout, where you drop out certain words in the sentence, also does work. Any other questions? Yeah.
So probably back to my previous question.
Yeah.
But we always feed the output, the prediction into the input during training time. So do you mean that what we should probably try is to like drop out some infection?
So what you actually should do is probably something like the structured Hinge loss. This is kind of a good training algorithm that will do well at optimizing over structures, but it's slower and a bit harder to train. So doing stuff like this kind of sampling algorithm where you sample from the model, or dropping out words. These are also very good options that are much easier to implement. So, yeah.
Compare the substitutional and solution together. I
Can you combine? Yeah, I think you could combine all of these together if you wanted to, but they all kind of solve the same problem, so you would very quickly see diminishing returns from combining them, I think. So when you decide which methods to implement, generally implementing methods that solve different problems is a good idea. And in this case, these are all kind of solving the same problem. So it might not help a huge amount. Yeah.
Like word dropout, isn't it the same as using dropout for, say, the embedding layer of your network in some sense? If you wanted to drop out the entire column instead of
So word dropout is quite different in that you're dropping out whole words at the same time, as opposed to regular dropout, where you're not dropping out whole words. So in regular dropout,
for the embedding layer.
yeah, but even on the embedding layer, if you're dropping out each node separately,
Yeah, like if you drop out the entire column instead of uniformly sampling for each one.
oh, that's equivalent.
That's exactly
Yeah, that's equivalent. Yeah. Although I guess there's two ways you can implement word dropout. One way is that you drop out words randomly. Another way is that you drop out types randomly. So there you might drop out all of the thes in your sentence. I don't intuitively know why dropping out all of the thes in your sentence is a good idea, but some people do it. So there's kind of two distinctions even within word dropout. Any other questions? Okay, I'll finish up then, and see you next Thursday.